Hi there, my name is Hannah Finney, and this is my student project presentation for Calculus 1 on iterative processes and the onset of chaos. Here's my name and my wonderful signature. And it is January 6, 2025, so let's dive right on into it. So the instructions for the presentation were to address our reasoning for our answers to questions 19 through 21. So before talking about the convergence and the oscillatory patterns of a function, I did just want to briefly touch on what my understanding of convergence is, in regards to calculus at least. So in calculus, convergence of a function means that as the input value approaches a certain point, the function's output value gets arbitrarily close to a specific finite limit. So all of that to say that as we input certain values, typically x, into a function, our output values will converge to one singular specific finite value. And I do not see that with our function with an r value equal to 3.2. Instead, we actually oscillate between two different values. And those values are 0.513 and 0.7995. And from the graph on the left, we can see that those values and their oscillatory patterns make like this nice lovely X. Or maybe a square, I guess I should say. So we can see that the output values graphed on the left, on the y-axis, bounce between two values rather than stay at one localized fixed point. And then on the right, I just have a little representation of what a graph might look like with output values graphed on the y-axis and input values graphed on the x-axis if the output values were actually to converge to a singular point. And to explain what I meant by the values oscillate between two distinct values, we'll talk about the oscillation of a function, cycles, and so forth. So the oscillation of a function refers to the amount a function varies between its extreme values within a given interval. Essentially to say, oscillation describes how much a function's output values will vary between its minimum, its absolute minimum, and its absolute maximum. But graphically, when we look at that, we're almost looking at like a diagram of a wave pattern. So we have the absolute maximum, almost equivalent to the peak of a wave, and the absolute minimums as equivalent to something like the trough of a wave. And then the period of that function, much like the period of a wave, can be measured as the distance on the horizontal or the x-axis between the peaks or the troughs of the wave. And it's the interval in which the function repeats itself. So for a 2-cycle, we see an iterative process where the iterations, the sequences of values produced, repeats itself after 2 iterations. So the first iteration will be equal to the third iteration, that will be equal to the 5th iteration, and etc., etc. And that's exactly what we saw in our previous function output when our R value was equal to 3.2. The iterative process oscillated between the values of 0.513 and 0.7995 in what is referred to as a 2-cycle. And then moving on to our next function, our next iterative process where we adjusted our R value to 3.5 from 3.2, we can actually see like almost more divergence occurring in that it appears like the process is actually bifurcated, because not only are we in a multiple cycle of some kind of oscillatory value, but it seems to have expanded to contain more values. And we can see that in my plot here, which I am very proud of. I thought it represented it beautifully, where we are now in a 4-cycle instead of a 2-cycle. So it does appear that our 2 values have both bifurcated to create a 4-cycle. And we can see that the peaks and the troughs now also contain these 2 values in that interval between them. So we are going to repeat every 4 iterations to the same values of 0.3828, 0.8269, 0.5009, and 0.875. So iteration 1 of 0.3828 will be equal to iteration 5, and that will be 0.828. Now, I was curious if you could also classify this as a dual 2-cycle or a double 2-cycle, but I think that's outside of the scope of practice for me. Okay, and then for our last one, for question number 21, we can see that this process obviously does not converge. In fact, I feel like I am in the inception of squares. But it's fairly interesting because this is a pretty beautiful graph, and I feel like with our human propensity for trying to see reason and disreason or pattern within chaos, that it does look like there is some kind of pattern there. That being said, when we go to our other graph here, we can really see how chaotic our iterations become with the output values. So I thought it was fairly, and this is when R goes to 4. And I thought it was fairly interesting because these graphs to me actually remind me of looking at the monitor, either the bedside monitor or the defibrillation monitor of a patient when they go into something known as ventricular fibrillation from something like ventricular tachycardia or vice versa. And so I got curious. I was like, that looks shockingly similar. So I Googled it and come to find out that there is actually active research being done on iterative processes in the cardiac conduction system, the electrical conduction system for cardiac activity. So I thought that was fairly interesting. But I digress. So we can see that our values did not converge to any particular one value, nor was I, in my limited experience and understanding, able to identify any kind of clear oscillatory pattern. So I, because I was curious, wanted to make a bifurcation diagram. And in this diagram, we can pretty clearly see what I was referencing earlier when our R value went from 3.2 to 3.5, of it looked like it had a dual bifurcation. So both of the iteration values, those 2-cycle values split, they bifurcated into a 4-cycle. And we can see that exactly past the point of, well, I don't know, probably 3.45 actually. So if we had graphed and iterated 3.45, maybe we would be able to see the same bifurcations. But as we progress further to around 3.55, probably, we can see it bifurcate again, which was actually not one that we had to plot, that we had to iterate. And so we can see it bifurcate again, each of those bifurcations that had bifurcated, bifurcate again into what looks like an 8-cycle or so. And then directly after that, it seems like that's where we have our chaos onset. And I thought this was pretty interesting to color it like this because I have it colored according to the bifurcations so that you can see the outlines a little bit better of where it appears to reconverge. Brings me to this diagram, which is the same bifurcation diagram. I just color-coded it a little bit differently. So this one I color-coded according to the R value on like a gradient for the R value. So as the R value increases to 4 from 3.2, we are getting lighter and lighter and lighter. And we can see very, very clearly where it diverges, but more interestingly to me, and why I made this diagram, is we can see where it converges. So it looks like around 3.63, and I really should have added on some additional labels in there, but around 3.63, it looks like we are reconverging from what appears to be like a very chaotic pattern. And then around 3.73, we are reconverging from what appears to be a very chaotic pattern. And about 3.83, we are reconverging from what appears to be a very chaotic pattern. And then around 4, it's just like, no, I'm kidding. I'm sure there's further reconvergence past that. But I thought it was pretty interesting too to see that from where we had the 8-cycle previously to right after 3.63, right around there, we have a 1, 2, 3, 4, 5, 6-cycle. So we are reconverging from an 8-cycle into a 6-cycle. And then after that, it looks like it might be a 5-cycle. And then after that, it looks like we have a 3-cycle. So we actually seem to be reconverging at set intervals. And I just think that that is the coolest thing. So I hope you enjoyed my presentation and my bifurcation diagrams because I really enjoyed making them. And I'll see you in the next one.